Hello, welcome to Flip. So today we are on ionic bonding, and an ionic bond is formed between a metallic and non-metallic atom, so that each of the atom can now gain its stable noble gas configuration, like in the case of helium, neon, etc. Okay, so what we want ultimately is to get either of this electronic configuration. So 2, 2, 8, 2, 8, 8, or 2, 8, 8, 18. Okay, so as long as we form this configuration, this means it's a noble gas configuration. It means it's stable. And every atom wants to form this because currently they are not very happy with their electron count. Okay, they just want to form this. Okay, how it's done is basically for group 1 and to group 3 metals. Okay, there are metals in group 1 and group 3. It's easier for them to lose 1 to 3 electrons rather than to gain 5 to 7 electrons. What do I mean? Because, for example, in the case of lithium, there's 1 valence electron now. It doesn't make sense for it to, for example, gain 7 electrons, right? That will take too much energy. Instead, what it prefers is to lose this electron instead, okay, and just give it to other people. Later we will see how the transfer works. But in this case, you can see that lithium, it makes more sense for it to donate this 1 electron than to gain 7 more electrons. In the case of beryllium, it has 2 valence electron, so it makes sense for this beryllium atom to donate this 2 electron away rather than to collect 6 more electrons, because they will take more energy. Same for aluminium, it rather donates these 3 electrons here than to collect in 5 more electrons to form 2, 8. Okay, it doesn't want that because it has too much energy to take in 5 electrons. Okay, so you can see that for group 1 to 3 metals, they really just rather lose their electrons in the valence shell than to gain electrons. Okay, that's the characteristic of group 1 to 3 elements. On the other hand, group 5, this is 5, okay? VII is 7. So for group 5 to group 7, they are non-metals. They rather gain electrons than to lose electrons, because currently their valence shell has quite a lot of electrons already. So they rather just gain electrons. For example, in the case of nitrogen, it has 1, 2, 3, 4, 5. So to gain 8 as the holy grail number, 288, it just rather gain 3 more electrons. Makes sense, right? For oxygen, it has already 2, 6. So it rather just gain 2 electrons. Similarly, for fluorine, it just gain 1 electron and it will be sufficient to form the 8 outermost valence electrons. Okay, so as long as they form this holy grail, they will do the easiest way to form it. For metals, they will lose electrons. For non-metals, they will gain electrons. Okay, let's see how an ionic bond is being represented. It's actually being represented by a dot and cross diagram. This one shows all the electrons. Okay, and this is the legend. So for the dot, okay, it's called dot and cross because it's made out of dot and cross to represent the electrons. The dot in this case represents the sodium electrons. Okay, you can count that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, as per the periodic table. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 electrons. Sorry, this is 11 electrons, 17 electrons. Okay, so you draw them as such. Okay, so this one I'll explain later. Let's draw this dot and cross diagram. So basically you can see that sodium has 1 valence electrons. So does it want to gain 7 more electrons? No, right? It will waste too much energy. So you rather just donate this electron to chlorine, who just happen to need 1 more electron here. Do you see? Okay, because chlorine's valence shell, the outermost shell, has 7 electrons. So to gain the formula, the holy grail formula of 2, 8, 8, okay, from its 2, 8, 7, it just has to gain 1 electron. Okay, and this is what is being done. Basically, whatever electron that the sodium is giving out is being accepted into chlorine. So how will this look like if you draw it out? Basically, this will look like this. Now the chlorine has now a decreased number of shells, because this, okay, let's draw together. This is its nucleus. Now this is its first shell. 1, 2, second shell. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now it's 10 electrons. Okay, maybe we shouldn't write this because we want to represent it officially. And now, because it has lost an electron, which is a good thing, okay, it becomes a plus. Why? Because electrons are negative in nature. When we lose electrons, we gain a positive charge. If we gain an electron, we gain a negative charge. Okay? So in this case, you can see that sodium actually loses 1 electron, so it gains 1 negative charge. This is +1, but we don't write the 1, we just write a plus. On the other hand, for chlorine, okay, this is what happens. This is nucleus, first shell with 2 electrons. So notice I'm using cross for chlorine atoms. Okay, so after the first shell, this is the second shell with 8 electrons. There's no change for this, just copying the same thing. Okay, 1, 2, okay. Finally, this is its third shell of electrons with 1, 2, 3, 4, 5, 6, 7, and the final electron is a dot. Because notice that this dot actually refers to sodium's electron, which means it came from here. Okay, you don't have to draw it this way. You can draw it anywhere, as long as it remains on the final shell. Okay, and this one has a negative charge because, as per this statement, when we gain an electron, as with what chlorine is done, we gain a negative charge. Okay, so there's a negative charge here. So what we have here is this is Na+, this is Cl-. Okay, and this is how we represent a bond between sodium and chlorine. It's not very obvious that this is a bond, okay, because this is just a dot and cross diagram. You can imagine that there's electrostatic forces between them, because now what you are forming is a positive charge having a interaction with a negative charge. Okay, but you don't have to draw this interaction. You just draw these two sort of boxes side by side and you are good, okay, with the charges included. Notice this one is a square bracket, so please do not draw the circle bracket. Okay, so this is one way to represent them, the ionic bond. Another way is to represent only the valence electrons, which is what a lot of some questions will ask you to do, because to just not draw the inside at electrons which do not react at all anyway. So you can see that it's the same thing. Okay, maybe I just draw it, I just push it up like this. You can see. Okay, so you can see that if I take into the final electron count, okay, I'm ignoring these 2 electrons. In this case, I'm ignoring the first shell and the second shell, which will result in this. Okay, and that's why there's some space between the nucleus and the valence shell. Okay, this is not necessary, but I think it's nicer and it's more accurate to draw this leave this empty space here. Okay, with the plus charge, of course, and 8 electrons. And chlorine, on the other hand, you have to draw them bigger because chlorine is bigger than sodium in terms of size, and the empty spaces also account for 2 shells that are not being drawn. Okay, and finally there are 8 valence electrons. One of them is a dot, okay, belonging previously to sodium, and now it has negative charge with the square brackets. Okay, and that is all for ionic bond. Next we'll talk about the properties and structures of ionic compounds.